Design of concrete structures. Let's solve another example in double reinforced concrete section. So in this example, we have a cross section like a 14 times 24 solid rectangular cross section with two compression rebars of number 7 and 4 number 10 tensile rebar. If F prime C specific strength of concrete is 5,000 psi and yield strength of steel is 60,000 psi, let's calculate the nominal and also design moment capacity of the section. So first of all, because F prime C is 5,000, so jump to the table and read out a beta 1, and then let's assume the compressive steel is yielding and then check it. So F prime S should be equal to Fy, or epsilon prime S at least equal or bigger than epsilon Y, and then check it. So the area of AS prime is, each of them is a 60, so two of them is 1.2 inches squared, which you can see here. We can call that AS2 as well. And number 10 is equal to, the area of number 10 is equal to 1.7, and four of them, it makes it like 5, area of tensile steel 5.8 inches squared, and we can call AS1 a subtraction of 4 number 10 minus 2 number 7, 5.8 minus 1.2 give us a 3.88 inch squared for AS1. And then we can calculate the height of thickness block, which is AS1 times Fy over 85% F prime C times B, and it just gives us a numeric value of 0.91 for height. The height of this block of stress, and then location of neutral axis is just C over beta 1. Beta 1 is 0.8, and it just gives us a neutral axis located at 4.89 inches. So let's see what's happened in terms of yielding. Epsilon prime S is a epsilon U, which is here. That's crushing point of concrete. 3 times C minus D prime over C. We just learned that C is 4.89. In this slide, minus 2.1, which is D prime here in problem statement, or 4.89. It just gives us epsilon prime S is equal to 0015. And if you get a epsilon prime S 15 is less than epsilon Y, which is 60 over 29,000, and it's 0.0020, and definitely it's smaller than. So compression steel does not yield. We need through the second degree equation to solve it. And if you remember, if epsilon prime S is bigger than epsilon Y, that's the compression steel yields. And if not, we have two options: trial and error, which is a Nielsen approximation, or exact method, or which is a second degree equation. We choose this one, which is more accurate. F prime exact method just gives us the second equation based off x is a neutral axis, so x and c are equal. We just make it like different, like x to not make a mess with this coefficient of this equation, and it just gives us a coefficient b and c. If we just replace the numeric value of problem statement in a, b, and c and solve the equation, it just gives us a equal to this numeric value 600 is equal to a negative 200 for 200,000. C is negative 261,000. And if you just replace that in the equation of ax squared plus bx plus c equals 0, it just gives us two roots of the equation. The negative one is not the answer, and the positive one is the location of neutral axis from top of the section, and that gives us 5.5 inches in terms of neutral axis exact location. So as soon as we have the neutral axis location, which is 5.5 from top of the section, can just jump in the equation of f prime c and just plug it in, and just gives you f prime s is equal to 5 almost 500,000. That's a something like 70, almost 76% of f prime c, f prime s, which is fy, which is 60,000 problem statement. So it just says your compression steel of these two number 7 ribbons. It's not going to, but it just reached something like 76% of yield. So most of the capacity of is something like retrieved, but not fully done. So the third step is nominal capacity, and that consists of two parts: a tensile domain, compression domain. Add them up together and just report it like a addition of two more. Then just don't forget it. Convert it to 12 inches is 1 foot, and it just divided by 1000 to report it by kilo. That makes it like 555.83 nominal moment capacity. M sub n is 555.83 kilopound feet. And if you just multiply that by a phi reduction factor of 9 for flexural member, and if it's ductile, we double check the ductility of the section later on. So that's our design moment. MU ultimate design is phi times MN. So if you just do the math, it just gives you MU ultimate design moment is 500.25 kilopound feet, and that's our final answer. We just need to check the ductility to see if we are allowed to use this reduction factor of 0.9 or not. So if you do so, let's first of all check the row minimum based off ACI code uh, version 2019. Row minimum is the maximum of these two terms, 1 or 2, and just we do based off f prime c. If it's less than 4,445 psi or bigger than that, you can use each of those two terms. So definitely our f prime c is 5,000 in this one, and row minimum first one is controlling. So if you just plug it in the first equation like that is, and compare row available is AS area of steel, which is 5.48 over BD times 14, which is here, and it should be bigger than row minimum, which is a 3 times F prime C over Y, which Fy is 60,000 and C is 5,000. If you plug it in, it just gives you 0.5. So our section available is smaller than ACI code. So we have the minimum requirement. Let's see the maximum requirement as well. So the maximum requirement ductility is just this table. If we have a number 60 steel, we need to double check C over D should be smaller than 375, and our steel is grade 60. So C over D should be smaller than 75 for grade 60 steel. So our C is 5 point, which is 24. Let's give us 0.2, which is definitely less than that. So ductility check is passed. We are allowed to use phi as 0.9 flexural member design. So our calculation is correct. Thank you. Solve more problem. concrete analysis of this section. Thank you.